All right, so today we're going to get into talking about exponential growth. We're going to talk about continuous compounding. So first, a little bit of review of last year when you talked about investing money. You did your P1 plus R over N to the NT formula. We're going to talk about that in just a second. But when you thought about investing money, that was compounded at certain times throughout the year. So let's say we have $50 that we are investing at 8% interest rate per year. So this is my year, this little number line here. That's 1 year represents 8%. So to figure out how much money we'd have at the end of that year, we just take what we have, we multiply by the growth rate, and then we can compound, we can measure, after 1 year, we could put 1 in for T. I could figure out how much we'd have after 2 years. I could put 2 in for T, 4 years, 10 years. So that's just kind of like your basic exponential growth formula. We take the rate, we add 1 to it to make sure it's growing, not decreasing, and we multiply it by what we start with. So let's say we now are compounding this interest twice a year. So what we're doing is we're taking that 8% and we're splitting it up into two 4% periods. So if I think about my formula and how that changes, I now have my same $50. But instead of doing 8% once a year, I split that 8% up into two even parts, but I'm compounding twice as often. So this becomes 2T. All right, so you can see as it compares to the formula above, instead of compounding 8% once, I'm compounding 4% twice. So now let's say we are compounding this quarterly. So we would take that 8% and we would divide it up into 4 equal pieces. So you can see this would be 2%, 2%, 2%, 2%. So how's that going to change our formula? We have the same $50, but instead of doing 8% once a year, we're doing the 8% 4 times a year. So that's where I would get that 1.02%. But instead of compounding twice a year, we're compounding 4 times a year. So you can see the overall percentage stays the same. We're just chopping it up into smaller pieces and compounding it more often. So it balances out. The more we compound, obviously, the more we're going to make, right? If we have more that goes into our multiplier, that goes into our formula, the bigger the number is, the more we're going to make on the other end. So now let's say we chop this up into 365 pieces. I'm not going to do that math, but this would become 1 plus 0.08 divided by 365. So we would take that 8%, we would cut it up into 365 tiny little pieces. And then I would compound it 365 times a year. So every day we would be compounding. So you can probably guess where we're going with this. But let's look back at our formula that you learned last year. We'll do a couple little examples. All right, so please pause and take a minute and write this down. I'm not going to wait too long for you, so please just pause and do that now. This is everything we really just talked about. All right, so I'm going to move on now. So please pause and get that jotted down. So let's say, just very straightforward example, we have $12,000, 9% interest that we are investing for 5 years, compounded quarterly. How much will we have at the end of this investment? So we go to our formula. We want to figure out what A of T is. We have P, 1 plus our rate, 9%, cut up 4 times per year. So 0.09 divided by those 4 equal installments to the NT power. So really just plugging it into our formula, we go into our calculator, we get about $18,726.11 when I did this out on my calculator. So keep that number in mind. That's our 9% if we're compounding it 4 times per year. All right, so that's again where this part of our formula changes. All right, this example is not great. I meant to change it this year. Credit cards, for those of you who have them, they don't carry over for the year. They're month-to-month kind of investment. So just kind of bear with me, ignore the actual question for a second. So let's say we owe $800 on a credit card, which charges 18% interest annually and compounds semi-annually. So semi-annually means twice a year. How much money will we owe after 1 year, assuming no more payments or purchases are made? So how much will we owe after 1 year? So again, very straightforward. The amount we owe after 1 year, so A of t, I guess I could put A of 1 there, equals my principal, what I have now or what I've invested or what I owe, 1 plus r over n, in this case n is 2, to the nt power. So I'm asking for 1 year, how much will we owe? So we go into our formula, go into our calculator, we plug it in, and we get just about $950. Okay, so that's review. So I'm hoping that comes back to that, rings a bell. Let's do a little more algebra here, so you can ignore that red arrow for now. I'm going to ask you another question in a second. So when will we owe twice the amount we owe now? So basically, I want to know when the A of t will equal $1,600. So when will that final amount double what we owe now? So we're still going to plug in everything that we know. So in this case, I actually kind of know the answer. We need to work backwards here. So 1,600 equals 800. And then we have the, whoops, not equals, times. And then we have our P1 plus R over N. So divided by 2 is 1.09. Sorry, I'm getting a step ahead of myself. Let me make that better. So we still have our 0.18 twice a year. Now, the only thing we don't know in this particular question is the t. So we're going to leave that as a t. Careful with your order of operations. We mentioned this, I think, early in this unit. That's the first thing we have to do. So now we have 2 equals 1.09 to the 2t. At this point, we have an exponential equation. To unlock that, I need to rewrite it as an exponent or as a log. So we have log base 1.09. And I can't write today on this thing. Log base, maybe it's because the log looks like the 1.09. 1.09, log base 1.09 of 2 equals 2t. And to get the t by itself, I just divide both sides by 2. So we have t equals log base 1.09 of 2 divided by 2 into our calculator, and we get about 4 years. All right, roughly. So in 4 years, we'll owe twice the amount we owe now. So what I want you to think about, and I want you to pause for a second while you try this. Same question. So when will we owe twice the amount we owe now? But what if we originally only owed $10? So how long will that take to get to 20? So I want you to try this one on your own. I'm going to pause. And then when you're done thinking about it, you can unpause and see what I have. So hopefully what we realized is that the answer is the same. This nature of exponential growth. It would take us the same amount of time to get from $10 to $20 as it would from 800 to 1,600, as it would from 1 million to 2 million. So that doubling time, no matter what we start with, is always going to be the same. So right off the bat, you can see right here, even after the very first step, the problem's identical to the one next to it. So keep that in mind for when we take our notes next class. It's a really kind of a helpful strategy, a helpful shortcut to think about. So on to the next page. I mentioned this at the beginning when we're talking about compounding more and more and more and more often. So let's say we do compound. We have an investment we can compound 365 times a year, where that n gets really, really, really large. Or what if we're compounding every hour? I don't know how many hours there are in here. I could figure that out. But what if we compound every second? So as that value gets bigger and bigger and bigger, this is that exploration we did earlier in this unit where I put an x here. So it was 1 plus 1 over x to the xt. And this is where our evaluation of this, when we started putting larger and larger numbers in for x, so basically when we started compounding more and more and more frequently, we discovered that this number turned into the number e. So our formula, whenever we have something that's compounding continuously, whether it's a financial institution compounding your money interest continuously, compounding that interest continuously throughout the year, or a much more common way we're going to see it is with population growth. We're going to look at that next class. When something is compounding constantly all the time at like a very slowly but surely rate, that's called the relative growth rate. That's when we're going to use this PERT formula, P times e to the RT. This E is our mathematical kind of representation of continuous growth. So real quick, we'll see what it looks like. This is the same question from the first page. So let's say you're putting money into a bank and they give you options. They're going to say, well, we can either compound this quarterly or we can compound this continuously throughout the year. You can see how this is going to pay off to our advantage. So we have A of t equals our principal, P e to the r times t power. And now just right into our calculator, no algebra to do. We plug it in and we get $18,819.75, I believe. When I wrote this down, I think I can read my handwriting yet. So a little more money than we would have made if we just compounded that little bit quarterly. All right, so the more we compound, the more it kind of grows on top of itself. So how many years would it take you to reach 50,000? Again, this is our kind of a working backwards. We know we want to get to 50,000 based on this $12,000 starting point. We still know everything except the t value, the time in this case. So very careful here. This is 12,000 times e to the RT. So our order of operations is really important here. So to get that exponential term by itself, the first thing we have to do is divide out by that 12,000. So I'm going to keep everything I'm going to keep everything as a fraction for now. So we could end up with some irrational numbers here, some decimals that don't really repeat nicely. So I'm going to keep this as 25 over 6, just reducing that down. And we have e to the RT. So this continuous growth happens so much with these exponential growth problems. This is what we mentioned earlier. It has its own log function. It has its own log, which is the natural log. So we have log base e of 25 over 6 equals 0.09 times t. And I'm out of space, so I'm going to go up here. We divide both sides by 0.9. We get t equals the natural log of 25/6 over 0.09. And we go into our calculator, and I got like 15.86 years, something like that. I know I didn't really tell you what to round to. So that's where the formula comes from. That's why this E happens so much. All right, we're going to talk about this when we get into our notes next class. But for population growth, the world population, the population of deer in Syracuse area, they don't just double every 6 months, right? Every 6 months, a bunch of deer don't just have a bunch of offspring and then the deer population doubles. It grows at a slow but steadily exponential rate. So that's why these population growth questions use the number E as their base, because it's a slow and steady but continuous growth model. All right, and we're going to skip these next two questions. We don't really need we could talk about anything. We're not going to hit on this for now. But next class, we will jump into exponential growth when discussing population. Okay, so that's it for your homework. Make sure you get these notes down. If you have any questions on the background here, please let me know, and I'll see you next time. Bye. All right, hopefully you didn't hang up. I changed my mind. We're just going to jot these notes down. It'll save us a minute in class just so we can jump right into it. Okay, so as I mentioned a second ago, with this population growth, population of people in our city, world population of deer, population of bacteria in a dish, there's no set time. We're not doubling every 5 hours, or we're not growing by 9% every year. We're constantly but slowly growing all the time exponentially. So our formula it's really just the same thing as the PE to the RT, but with population, a lot of times you'll see it as an N instead of a P. But same formula. N sub 0 is our initial population. R is our relative rate of growth. So relative growth rate really just means the growth rate based on how many things there are there now. So like if we put some bacteria in a dish and it starts with only 2 bacteria, they're not going to be growing as fast because there's only 2 of them to replicate. But if there's 10,000 of them, they're going to be growing at a much faster rate because there's more to grow on. So the relative growth rate is kind of all based on the increase based on the amount that's there. Okay? So there's our formula. We're going to jump in right on this page next class, and I will see you soon.